Okay, let me mute everyone. Okay, today I want to introduce some of the famous CNN architectures. There are several newly developed architectures in CNN domain. Let's see one by one. As you can see in this timeline, they mentioned the date that each of these CNN architectures are introduced. The first one, resnet, which is the first CNN architecture, introduced in 1998, but most of the attention to the CNN starts from 2012 when the first modern CNN architecture is introduced, AlexNet. After 1 or 2 years, several advanced architectures are introduced, VGG, Inception version 1, resnet, and network in network. Then in 2015, Inception version 3 or Google Net is introduced. After that, Exception and Inception version 4, Inception with resnet. These are the timeline of introducing different architectures. Let's check each of these architectures one by one. Before that, in this table you can see the size of different architecture. For example, VGG16 model on the hard disk takes 528 megabyte, and this is the accuracy of this system over the ImageNet dataset. As I told you, ImageNet is a very huge dataset with millions of images, and they are organized in 1000 categories. In one competition, different participants proposed their architecture in order to classify the images in this database or dataset. There are two evaluation metrics. Top 1 accuracy, it means that the output of the system will be one label and it can be checked with the actual label. For the VGG16, the accuracy is 71%. So in 71% of the times, the predicted label and the actual label is the same. As you can see, for the other advanced architecture, this accuracy become more and more. For example, Inception resnet version 2, the accuracy become 80%. Another accuracy metric is top 5 accuracy. It means that the output of the neurons in the last layer will be checked and the 5 neurons with the highest probability will be selected. Then if the actual label exists in one of them, we accept it. We say that the system correctly recognizes this image. So for the VGG16, 90% of the times the actual label exists in the 5 label that is predicted by the system. The 5 label with highest accuracy or 5 label with highest probability. If you remember, in the output layer of a CNN, we have some neurons, and the number of neurons is the same as the number of class labels. So here we have 1000 neurons in the last layer of each of these architectures, because we have 1000 class or categories in ImageNet. So when we give one input sample to the system, all of this output have some values. We check them and select the 5 neurons with the highest output values. And as you know, each of these neurons is corresponding to one of the labels. For example, one of them indicates the input is belongs to class cat, class dog, class sheep, car, airplane, or any other classes. We have 1000 categories. So we find the 5 neurons with highest output and check their label. If the label is equal to the label of the test image, we said that this image classified correctly. So this is the meaning of top 5 accuracy. Instead of only predict one label, we consider 5 most predictions values from the output of the system, and if one of them is correct, we said that this image is correctly classified. So as you can see here, in 95% of the times the image is correctly classified by Inception ResNet version 2. And this column shows the number of parameters for each of these architectures. As you can see, the VGG16 has 138 millions of parameters. These are the number of weights that the system should be trained from the training set, and it is very huge. But in the modern architecture, the number of parameters reduced. However, the depth of this architecture are increased. In the VGG16 architecture, we have only 23 layers, but in the modern architecture, as you can see, for example, 500, 100 layers, 160 layers exist. So even when we increase the number of layers, we expect to increase the number of parameters, but by some advanced methods, as you can see, the number of parameters in the modern architecture are much more less than the early architecture like AlexNet or VGG16. Let's check the first architecture, LeNet 5. This is the first time that someone used CNN. So in fact, the author of this paper introduced this convolutional neural network. The input image is very small. It's a grayscale image of numbers between 0 to 9. So the input image is 32 by 32 pixels, and as you can see, it is grayscale. Then they give it to the 2 convolutional layers. The first convolutional layers use a 5 by 5 kernel, and the activation of the neurons is tangent hyperbolic. We never use this tangent hyperbolic as the activation function for the neurons anymore. We use ReLU or rectified linear unit, but in the early days they used this tangent hyperbolic from the neural networks idea. So then the output of this convolutional layer is given to the average pooling by with kernel 2 by 2, but in this architecture the average pooling weights are also learnable. So in the recent days we never use a average pooling with learnable weights, but for this time they introduce an average pooling layer with learnable parameters. Then the output of this downsampling features is given to another convolutional layer to extract more complex feature, and again after performing tangent hyperbolic on the output, they give it to the another average pooling, and finally they give it to the 3 fully connected layers. The first fully connected layer has 120 neurons, the second one has 84 neurons, and the last one has 10 neurons according to the 10 different classes. So this system classified handwritten digits between 0 to 9. So we give it a handwritten digits like 0, 1, 2, 3, and the system classify it according to the features that are extracted here. 5 in the resnet indicates that we have 5 layers, one here convolutional, this one, and 3 for the fully connected one. However, these 2 layers in the resnet also are trainable. This architecture has 60,000 parameters. And as you can see, this architecture has become the standard template. The idea of stacking convolutional layers and pulling layers together and then end it with some fully connected layers will be used in the other advanced CNN architectures. So all of them get their main idea from the resnet 5. resnet introduced in 1998, but the main attention to the convolutional neural networks started from 2012 when the AlexNet is introduced, and it won the ImageNet competition. The input layer size is 224 by 224 and the input images are RGB. Then apply a convolutional operation on this input image. As you can see, the kernel size is 11 by 11, a very huge kernel, and they also introduce using rectified linear unit as the activation function. Then this extracted features is given to the max pooling, and the kernel size of the max pooling is 3 by 3. But the max pooling is not trainable anymore like all of the recent architecture. Then the downsampled features are given to the another convolutional layer. In this layer, the kernel size is reduced to 5 by 5. So in the early layer, they try to extract large features in a large neighborhood. Then they try to focus on a small and a smaller part and give it to again a max pooling 3 by 3. After that, they give it to some convolutional layers which are cascade to each other. So one convolutional, this multiply by 3 means that there are 3 convolutional layers. So all of them has 3 by 3 kernels. So we have one convolutional layer here, 1, 2, and 3 here. So we have totally 5 convolutional layers in this architecture. So 3 convolutional layer with 3 by 3 kernels are here. Pay attention that between each convolutional layer and the next one, we have to perform the nonlinear transformation. If you have one convolutional layer here and another here, and you want to put the input of one of them to the other one, if you didn't put a ReLU or one nonlinear activation between them, then it doesn't mean anything. It seems that you perform one convolutional. So it is important to, between each convolutional layer and then between two consecutive convolutional layer, put some ReLU layer. So in your program never mention two convolutional layers after each other. Between them you should put some ReLU. And as you can see, we have 1000 neurons in the last layer because we have 1000 classes, but before that we have two fully connected layers with 4096 different neurons. So there are 4096 neurons here and here also, and each of them are connected to all of the other ones. So one neuron from this layer is connected to all of the neurons of this one, and also one neuron from this layer is connected to all of the neurons in this part. So we have millions of weights here. 4096 times 4096 times 1000 only here. And also from this part we have a lot of learnable parameters or learnable weights. So as you can see, this architecture totally has 60 million parameters. So AlexNet has 8 layers, 5 convolutional and 3 fully connected. So as you can see, AlexNet just stacked a few more layers on LearnNet, and also one of the novelty of this architecture is that they are the first ones that who use rectified linear unit as activation functions in CNN. And from this point everyone use only rectified linear unit, but before that they use tangent hyperbolic in the LearnNet 5. So we can get some idea from this architecture. Till this point in the previous example that I solved, we use convolutional ReLU max pooling, then convolutional ReLU max pooling. But as you can see, we can use convolutional several times after each others. But don't forget to put a ReLU or rectified linear unit between them. Because every time that you use max pooling, we perform downsampling on the features. So the feature set becomes smaller and smaller. So we have to after a few times that you perform max pooling, the size of the feature set becomes very small, so you have to stop after a while. But we can perform several convolutional after each others in order to extract more and more complex. The output of one convolutional layer is connected to another convolutional layer, and there isn't any max pooling between them. Okay, let me back to you to answer your questions. You can ask your question now, my friends. So, meanwhile, the other students, do you have any question?
Sir, can you explain the relay unit, ReLU?
ReLU is a simple activation function with these properties. If the value is positive, we keep it. The output of the function is the same as the input when the argument is positive. So let me, for positive value it is the same as the input, but for the negative value it will be 0. So the ReLU discard every negative features and map them to the 0, and for the positive one it doesn't change them If it is 100, the output is 100. If it is 1, the output is 1. But if it is minus 1, minus 10, minus 100, all of them are mapped to 0. This is the rectified linear unit operation. Okay, let me come back. Let's move to the next architecture, VGG16. The AlexNet is the winner of the competition at 2012, I think. So this is the author name, Alex Dirijovsky, or something like that. In the VGG16, as you can see, they introduce a more deep architecture. First, the input layer is the same as the previous one. The images are 224 by 224 and RGB format. But here, as you can see, the first difference is that all of the convolutional layers have the same kernel, 3 by 3. But in the previous one, in the beginning they use a large kernel and then they reduce it to 5 by 5, and finally in 3 convolutional layers they use a 3 by 3 kernels. But here all of the convolutional layers have the same kernel size, 3 by 3 only. And another point is that they use several bunch of the layers. As you can see, there is a multiply 2 here. It means that two structure like this is concatenate to each other. So first a convolutional 3 by 3, then ReLU, again convolutional 3 by 3, then a max pooling, then come back again another 3 by 3 convolutional layer, another 3 by 3, and another max pooling. Then it will give it to another bunch of the layers. In this bunch of the layers, 3 consecutive convolutional layers exist, and as you can see, after 3 convolutional layers we have 1 max pooling. Again, this part repeated 3 times. So we have 1, 2 multiplied by 2, 4 convolutional layer here, 1, 2, 3 times 3, 9 here, 9 plus 4 is 13 different convolutional layers. We have 2 max pooling here, 3 max pooling here, so we have 5 max pooling. And in the end of the architecture they have the same layers as the previous one, 2 fully connected with 4096 neurons and 1 output layer with 1000 neurons corresponding to 1000 categories in the ImageNet. So one of the novelty of their work is increasing the number of layers. They find out that by increasing the number of layers they can improve the performance of the deep neural networks. VGG16 has 13 convolutional and 3 fully connected layers, and between all of them we use ReLU layer. And as I mentioned, in all of the layers, in the convolutional layers we use 3 by 3 kernel, and for the all of the max pooling they use 2 by 2 kernel size. It has 138 millions of parameters. Also they introduced another version, they mention it VGG19, so I think they repeat this part 4 times in the VGG19. So VGG16 has 13 convolutional layer and 3 fully connected, so 3 plus 13 is 16. This is the reason that they mention VGG16. They counting the number of convolutional layer and the fully connected layers. 13 plus 3, 16. in the VGG19, I think they repeat this bunch of the layers 4 times. Before I move forward to the other advanced architectures, let's see how we can use the exist architecture in Matlab. These architectures are publicly available on the internet, and you can download them, use that architecture. Not only the architecture, you can use all of the learned information inside this model. This model is trained over millions of images, so we can use that information that exists inside this model. Instead of train a model from the scratch, we can use a pre-trained model in our project. First of all, if I want to use this architecture VGG16 in Matlab, since the number of parameters is very high, for example 138 millions of parameters, I need to provide millions of images. But in the project that I explained last week, we have only a few samples, for example 1000 samples. So it is not sufficient to train a deep architecture like VGG16 by using 1000 samples. So how can I use this architecture, which is more advanced than the previous simple architecture that I explained last week? And how can I overcome the problem that I have only a few and limited number of samples? There are two ways. First, provide more samples for your model, which is very time consuming, and also maybe it is impossible for us. Or you can use a pre-trained model and adjust it to work with your new situation. We call this procedure transfer learning. This is the main idea of the transfer learning. We have a source of data with a lot of samples. So we create a model over this huge data set, and then we use this trained model and perform some adjustment over it to make it suitable for our new task, for the another database that I have, and it has a very limited number of samples. So this is the difference between traditional machine learning approach and transfer learning. In the traditional machine learning, between two different tasks you didn't share anything. So these are isolated single task learning. So knowledge is not retrained or accumulated. Learning is performed without considering past learned knowledge in other tasks. But in the transfer learning idea, as you can see, we train a model over a data set. Then this model learns some knowledge, and that knowledge can be used for another data set and another task. This is the idea for transfer learning. We say that in the early layers of the CNN, they extract some features, and in the end of the CNN we give it to the classifier. So these features that are extracted from the image in the another task maybe can be used in the new situation that I have. Maybe that features can be used to discriminate between the images that I have in my target database. So in order to reutilize these extracted features, I can only replace the last layer of the CNN and put a new layer instead here, or give it to the another classifier like SVM, I put one fully connected here, and only I need to train the weights between this new fully connected and the previous one. Only the weights between this part should be trained. The other part of the system is trained before over a huge database. So only a few weights that are exist between this layer and the previous exist one should be retrained. We call it fine-tuning. So these new weights can be updated by using the images of the target database that has only a few samples. So let me redefine the problem. I have some famous architectures and I want to use them in my project, but the number of samples that I have in my project is very limited. This famous architecture needs a lot of samples in order to successfully train a model. Therefore, instead of train a huge architecture from the beginning, I can use the pre-trained model and only change the number of samples in the last layer of the CNN to make it compatible with my new target domain and new situation that I want to create a model for it. For example, I have a pre-trained model over ImageNet and the last layer has 1000 categories. I want to use that architecture for my, for example, cat and dog classification problem. So in my new problem, I have only two categories. I have to remove the last fully connected. This last fully connected should be removed. Another fully connected with two neurons should be replaced. And then these two neurons are connected to all of the neurons in the previous one. And this weight should be learned. I can learn this weight by using the target database. The database that is only includes some images from the cat and dog. But the remaining part should be fixed. Actually, there are two approaches. They can be fixed. We call it frozen. We froze all of the previous layers weight, so they never change. Only we change the weights between this new layer and the previous one. Or we can also change them, but with a very smaller learning rate. For example, the learning rate of this layer will be 1, but the learning rate of this one will be 10. So we use actually 10 times the learning rate of this one should be 10 times larger than this one, or 20 times larger than the learning rate of these layers. This is the general idea of transfer learning. Let me show you how we can perform it in the Matlab. First of all, you have to download one of the exist architectures. In my system, I download all of the architectures before, so it is very hard to show you. Let me show you one example. From this add-ons, you can download some new package and add it to your Matlab. Let me see. Matlab pretrained CNN models. Let's check it. These are the available pretrained model in Matlab, VGG 16, 19, AlexNet, and a lot of other architectures exist. In this column, you can see the depth of these architectures. Here we have 16 layers, 19 layers. AlexNet has 8 layers. As you can see, some of them has a very deep architecture. The size of them in the hard disk, or now in the you should first download them. These are the number of parameters in millions. As you can see, 138 millions of parameters for VGG16, 61 millions here. But some of them has a fewer they have a fewer parameters. And this is the input image size of these architectures. Most of them are 224 by 224 or similar to this one. We can easily convert the size of the input image. And in this figure you can see a comparison between different architectures. This is the accuracy. So the AlexNet accuracy is near 54, I think. If we check the center, I think this is the top one accuracy. So let's check, for example, for VGG16 it should be 71%. Let's check it. VGG16, yes, 71%, the center of this circle. And the size of this circle is related to the number of parameters. So as you can see, if the VGG16 and VGG19 are they have a lot of parameters, 100 million parameters, but MobileNet or this ShuffleNet, they have a few number of parameters, so they can train faster. They need a smaller number of samples in order to train successfully. So when the number of parameters is huge, you have to provide more and more samples during the training, and also it takes a long time. And in this part, this is the relative prediction time. So as you can see, AlexNet take 1 unit of time to predict a sample, but this architecture takes 6 or 7 unit of time. So it is 7 times slower than the AlexNet, or this one, which is one of the best architecture, resnet. The accuracy is very high, 81-82%, but it is 40 times slower than the AlexNet. But this one, for example, DenseNet, it has a good performance, and its speed is also relatively acceptable. So this is a comparison between different architectures, and these are the names of this architecture in Matlab. When you want to load one of them, you can mention that name. For example, VGG19. Here, net equal VGG19. If you didn't download this package before, as you can see, it mentioned an error. This VGG19 requires the deep learning toolbox model. To install this support package, use the add-on explorer. So you click on it, the add-on explorer will be opened, then you download and install it. However, I don't want this architecture. This is a very huge and slow one, but I only want to show you how we can add one architecture to the system. Okay, here you select install, and then after a while, after 5 steps, download and install this one. Okay, you have to create a Matlab account. I don't remember my password. I think it should be this one. Okay. Okay, it takes some time. After you follow the instruction in this wizard, you can successfully download a package and add it to your system. For example, I have VGG16 on my system. I downloaded before. I load it and I put it in the variable net. Now I can see already what happened. The system is busy. Let me check another smaller, small size architecture. GoogleNet. Okay. As you can see, after I load the GoogleNet, one of the famous architectures, and put it in the net variable, the net variable has some properties: layers, connections, input names, and output names. Let's check the different layers of the net. So net point layers. As you can see, we have 144 different layers in the GoogleNet. GoogleNet is one of the advanced architecture with a very high and good performance. But the size of the GoogleNet architecture in the hard disk is smaller than the resnet, the VGG16. Let me check it. GoogleNet, where are you? 27 megabyte, but VGG16 size is very high, 515 megabyte. So when I try to open this one, it takes a long time, but this one is much more faster in my system to load it. So each layer has a name, some description, and as you can see, there are a lot of convolutional layer, ReLU layer, convolutional, ReLU, convolutional, ReLU, some max pooling, and some other type of the advanced layers. And in the end of the architectures, we have fully connected layer with 1000 neurons, and a softmax layer, which, as I mentioned, the softmax layer compute the probability of for each of the output neurons, and then classification output select the select the neuron with the highest probability. In order to perform transfer learning, I have to replace these layers, this one and this one, with some new layer. Let me show you. I have a database and I load it, I split it to terrain set and validation set. These are the same as the previous examples, and here I load one of the architectures that I need. I want to use that architecture for the transfer learning. So a pre-trained model of the architecture will be loaded into the memory, and we only want to change the last layer. For example, I want to perform a new classification task. So I have to find the last layer of the existing architecture and replace it with some new layers. Let's see how we can do it. So this is one of the architecture that I read and put it inside the net. First of all, how many categories we have in the target database? We can find it by using categories function. I give it the, let me run it line by line for you. I'm using a database contains some breast cancer images. We have only 2 categories in this image database. So let's see what is the output of this line. Sorry, first have to split the database into, you can see the number of classes in my database is only 2. So the categories output give us a cell. These are the name of the 2 categories, cancer and no cancer. If you have more categories, for example you have 10 categories, then this number of classes will become 10. A CNN in Matlab represents by a data structure contains some layers and their relationship and their connection. Now we want to create a new architecture. I use layer graph and give the pre-trained model as the parameter to the layer graph. So now I have a new architecture with the same architecture as the pre-trained model. Here I declare a new fully connected layer. So fully connected layer is the name of the function. This is the number of classes that I compute here, and this is the name. The name is arbitrary, and these 2 parameters are important. I'm using learning rate factor weight 10 times of the other layers. As I told you, when you want to retrain or fine-tuning your model, you can freeze the early layers weight, or you can increase the last layer learning rate more than the other ones. Here I mentioned that the last layer learning rate should be 10 times of the previous layers. So this new layer that I create and name it new FC layer, the learning rate for this layer is 10 times of the other layers. How many neurons we have here? Only 2, exactly the same as the number of categories that I have in my terrain set. Now I mentioned that replace this layer in the L graph with which one? With this one. What is the name of the layer that I want? This one, loss classifier. So the name of the corresponding layer should be mentioned here. So if I'm using the GoogleNet, for each of the different architecture, the names are different, so you have to check the name of the corresponding layer in the architecture that you want to use for transfer learning. In this example, I'm using GoogleNet. I will check the different layers. In the last of the architecture, we have a fully connected. I want to replace this layer with my new layer. So check this name and copy paste it and bring it here. So replace layer this new fully connected instead of this one. This is one step, and as I told you, this last classification layer also should be replaced. So I create a new classifier layer. I name it anything. This is the name and this is the name of the new fully connected. These are arbitrary. So the last, in this example, output layer should be replaced by this one. The other layers are copied from the original net. So now I have a new architecture which is based on the GoogleNet, but I adjust the last two layers, or in fact the last fully connected layer and classification layers. I will explain about the data augmentation. This is the training options, and as you can see, we train the network again over the, and this is the new architecture that I create. This is the options and this is the train set, but augmented train set. I will explain this part later. And then you can check the classification accuracy like the previous one. But what is the data augmentation? When you want to train a model, you offer each image several times. After in each epoch you offer each image one time, so we repeat this operation with multiple time of epochs. So in order to make the system to learn more and more advanced features from the image, we can change the a small part of the image and give it as a new image to the system. So they mentioned these techniques as data augmentation. For example, you can rotate it. For example, this is a cat image in my database. Instead of give it this image several times, next time I will give it this image, which is rotate to the left or rotate to the right or zoom. All of them are the same. These are a cat. So from this image or this image, each time system learn more and more different images, different features. As you can see again, this is the flip of the image or rotate of the image. So here they give it the original image by some rotation, translate it to the up, translate to the down. So this is again an image of the cat, but without the legs. This is the cat without head. This is some part of the cat. So each time we give one of these samples to the system, so system every time learn different type of the features instead of give it always the same image. So in order to perform it, we can use augmented image data store function, but here I didn't perform any augmentation operation. Only we perform resizing. Input image of the CNN should be the same size as the input layer size. Check it. In this architecture, the input image should be 224 by 224 and it should be RGB. But in my database, the size of the image is different. In order to make it possible to fit that image into the system, I will first compute the size of my images. Where did I do it? Okay, here. I give my image database terrain and I ask it to resize it to the input size that I have from the first layer. If you check this one, you can see it is the same as this number. 224 by 224 by 3. Now I mentioned that only keep this part. So my image terrain set will be resized to this size. Also, my image are grayscale. I ask it to consider it as a RGB by this parameter. So this is the way that we can convert an image with different size and make it compatible to feed it to the exist CNN. I should do the same thing for the test set or validation set, and there isn't anything else. Finally, we print. I compute the confusion matrix. I will explain it in another videos, but now I can train it with my only target database. My database contains some breast cancer image. In fact, these are 2 lines. One of them is not necessary. Or let me run it for the MRI image, because I think the MRI image database is smaller. Let me see. Can I show you the result? Generally, training a CNN can take hours or even days. If you have graphical processing unit on your laptop or your computer GPU, then Matlab can use that GPU in order to enhance the operation and do it much more faster, for example 10 times or 20 times faster than the running the program on simple CPU system. I have a Core i5 CPU, but I don't have GPU on my laptop. So as you can see, every time that you want to run a CNN, it takes 12 hours, even when we have a small database contains only 1000 images. But if you have GPU on your system, you can easily run it in, for example, 10 minutes. It seems that it doesn't answer in a reasonable time. I will let my system to work on it and record it. Let's see what happens. It seems that it wants to start up. Okay, you can ask your question meanwhile the system try to train.